this computer. Okay, so I start the recording and we will start our lecture. Sorry about that. You're probably familiar with the Zoom interface, so you can use a chat, okay, and you can also, I prefer you turn on your computer and ask me a question, okay, but make sure you mute yourself. Okay? If you don't mute yourself, we will have noise interference. Huh? Okay, so mute yourself, or I can see, I can mute all. Okay, so I muted all. Yes. Okay, and then I will start. So remember, last time we had this inquiry question, and we asked about the balloon and why it sticks to the wall. So let us see what really happens. Okay, so with this illustration, so open link. And okay. You can still see my screen. You can still see my, okay. Can you see my illustration here? Huh?
Yes.
Okay. So basically, if you are wearing a shirt, okay, and the shirt is normally neutral, so you have equal positive and negative charges. Same thing if you have a balloon. You can, the balloon is originally neutral. It has the same number of positive and negative charges. But if you rub it against your shirt, it accumulates negative charge. Okay. Now, if you bring it a little bit, it will go back and stick to your shirt because the negative charge on the balloon will attract the positive charge, or the balloon will be attracted to the positive charge. Okay. But if you bring it close to the wall, so you bring it close to the wall, notice what's happening. So the negative charges are getting away from the negative charge of the balloon, and they leave behind the positive charge that is left behind attracts the balloon. Okay, and so you have a force of attraction between the negative charge on the balloon and the polarized molecules or atoms on the wall, so that the positive charge is closer to the surface, the negative charge is away from the surface. So this is what is happening. And the same thing is happening when we had the illustration of the wood. Remember, yesterday I showed you when you charge two balloons, they will have both negative charges, so they will repel each other. But if you bring them close to a wooden stick or a wooden bar, they will stick to it. The wood is neutral, and so what will happen is, because the negative charge on the balloon is making the positive charge of the molecule stay on the surface, and the negative charge of the molecules go away from the surface a little bit, okay, and you will have the force of attraction, okay. So actually this experiment is not a new experiment, and this was done by okay. So this was done by Benjamin Franklin, who lived in the 1700s. He basically performed an experiment where he took a glass rod, okay, and he rubbed the glass rod with with silk, or and he notes that if you have the two glass rods and both of them are rubbed with silk, and you bring them together, they will attract each other. And so what is really happening, you have a positive charge, in this case on the glass rod. So this is a glass rod, you have a positive charge, and the positive charge here and the positive charge here on the two glass rods, they will cause them to attract each other. However, he notes he also notes that if he rubs a plastic rod with, in this case, so a plastic rod with wool, he notes that also he observed the same thing, the two rods will attract each other, okay, but obviously he did not know that this is negative charge in this case and positive charge for the glass rod. But what he did an experiment where he rubbed a glass rod and he rubbed a plastic rod, and he notes the opposite. He notes that they will repel. So here in this case, so here they repel each other, and here they repel each other. But here he notes that they will attract each other. Okay, so the positively charged glass rod and the negatively charged plastic rod attracted each other. Okay, and so what he used a convention. Okay, and he said, okay, the electric charge that is on the glass, he called it positive charge, and the negative charge and the charge on the rubber or the plastic rod, he called it negative. And since then, we stick with this convention that Benjamin Franklin came up with, that the charges that accumulate on a glass rod are positive, the charges that are accumulating on a negative rod are negative. Okay, on a plastic rod are negative. Okay, and so we know there are positive and negative charges. Most objects around us are neutral, so they are constituted of atoms and molecules. And so usually these atoms and molecules are, they have the same number of positive and negative charges, meaning they have the same number of protons and electrons, and hence they are neutral. Okay, so in this case, we say that the object is electrically neutral, or we can say there is no net charge on the object, or we can say the positive and negative charges are balanced. Okay, so in most cases, the objects that we are dealing with are not charged. Okay, however, if you charge an object by rubbing or by other means, okay, now this object is charged, and meaning it has either more positive charges or more negative charges. And so what we have a charge imbalance, or we can say the object has a net positive or negative charge. So let's assume, for example, here an object has 5 more positive charges and 2 more positive charges than the negative charges. So usually we represent the object by just showing 2 positive signs, meaning that we have only 2 positive charges on this object. So assume this is, we do not keep account of all the charges, because that will be billions of charges if you count all the electrons and the protons in the atoms and molecules. So we only represent the net charge, whether it's positive or if it's negative. So in this case, we have 3 more negative charges on this object, and we only show the net charge on the object. So in this case, we have 3 negative charges. So we only, usually in problems, we only show the net charge on an object. Okay. So please feel free to either use the chat, let me see if I can see, or use your microphone in order to unmute yourself and ask any question. Okay. All right. So how do we determine if the charge that is accumulating on an object is negative or positive? We know if we rub a glass with silk, we end up with a negative charge and a positive charge. The glass will have a positive charge and the silk will have a negative charge. And the way we do that, we look at this diagram. This is what is called a triboelectric series diagram. Okay, it has many elements, very common elements, from the skin, leather, and so on. Okay, and we have a positive red arrow pointing to the top and a negative blue arrow pointing to the bottom. Okay, so silk, we are rubbing silk with glass. So silk is here. Okay, the glass is here. Usually the material that is closer to the top of the diagram will acquire a positive charge, and the material that is in the lower or the other end of the diagram will acquire negative charge. Okay, so if you rub glass and silk, glass will have a net positive charge, and the silk will have a net negative charge on it. Let's take another example. Okay, let's assume we rub fur and plastic. Okay, so fur is, let's assume it's made of wool. So this is wool here, and the plastic can be rubber or can be polyester. So it's here. So clearly the polyester or the plastic will accumulate a negative charge, and the wool in this case, whether it is wool and cotton or whatever, the fur will accumulate a positive charge because so this is the wool in the diagram, in the triboelectric diagram. This is acrylic or plastic, it can be polyester or anything, and it accumulates negative charge. Okay, so using this triboelectric series diagram that was obtained experimentally, we can determine which material accumulates positive and which material accumulates negative charge. Okay, any questions? All right. All right, so you are familiar with charges. You have studied this in high school. Obviously, if you bring positive charge, two positive charges, they will repel each other with forces that are opposite in direction and equal in magnitude. So if you have two protons, for example, and they will repel each other, assuming there are no other forces of attraction or repulsion around them. Same thing, if you bring two electrons, two negative charges, they will repel each other, and they will repel each other with force. So this is actually, this is a Newton third law pair, because these forces occur in pairs. They are opposite in direction and equal in magnitude. Okay. However, if you bring a negative and a positive charge, they will attract each other. Again, the forces are still opposite in direction, as you can see. This is a force vector, so vector has a magnitude and direction. The directions are opposite to each other, and the magnitudes are the same, even if the charges are not the same. So even if you have Q1 here and Q2 here, and they are different, Q1 is different from Q2, and as long as Q1 is negative charge and Q2 is a positive charge, they will attract each other. Okay, so the general rule that you are familiar with is charges of the same sign repel one another, and charges with opposite signs attract one another. Okay. All right. Now, if you rub two objects, the question arises, will the total charge be the same? I mean, will the total charge change if you take the object, the wool, for example, and the glass rod, or the silk and glass rod, or wool and the plastic rod? Do you think the total charge will change if you add the negative and the positive charges on the two objects? What do you think? You can use your microphone, okay, or your chat, okay. All right, so Lanud and Shamma and Al-Hanouf, they say no, they do not change. That's true. Okay, charge is always conserved in an isolated system. So if we consider this as an isolated system, let's assume the human being here does not introduce any charges. Okay, if we rub these two objects, one of them will end up being negative, the other one being positive, and actually, if you start with the total charge initially, for example, is equal to 0, okay, of the two objects. So the net charge is 0. After you rub them, and you also add the net charge, so this is before, also the net charge after is going to be also 0. So basically, if you end up with 100 electrons on the rod, for example, or 100 electrons on the plastic, or let's say in this case, you have 100 electrons on the wool, you will have 100 missing electrons from the rod in this case. So actually, we have a transfer of charges from one object to another, but the total charge is the same. Okay, so we say this is a principle of charge conservation, or charge conservation law. The charge is in the change in the amount of electric charge in any volume of space is exactly equal to the amount of charge flowing into the volume minus the amount of charge flowing out of the volume. So if you take a system, okay, and that has a charge Q, okay, and if you bring in Qn, and but somehow you take out from it, then delta Q, the change and the charge of this system. So in this case, is not isolated system because you're putting in a charge and you're taking out a charge. Delta Q is going to be equal to Qn minus Q out. Okay, so this is the law of conservation of charge. And if the system is isolated, like in this case, so if the system is isolated, so this is isolated. So in this case, delta Q is going to be equal to 0 because Qn is equal to 0, Q out is equal to 0. That means the charge of the system is constant. Q is going to be constant. Okay, so this is the law of conservation of charge. So now we can add to the previous laws of conservation that we have observed before. Okay, any question about the conservation of charge? Okay, so charge is conserved. Charge cannot be created or cannot be disappear. It's just usually transferred from one object to another or from one molecule to another. They don't just disappear or they are not just created. Okay, so in an isolated system, the total electric charge is always conserved. That means the charge is constant, or we can say the change in charge delta Q is equal to 0. Okay, so let's take an example. Let's assume we have two similar metallic spheres, and one of them has a charge Q2 and one of them has charge Q1. And let's assume in this case that Q1 is larger than Q2, and the total charge in this case Q is just equal to Q1 plus Q2. So this is our system here of the two spheres. Okay, let's assume somehow we bring the two spheres together. Okay, and they are exactly similar spheres. Okay, so if they are touching, clearly the charge is total charge Q is still going to be equal to Q1 plus Q2. So delta Q is still 0. So the charge Q after they touch is Q1 plus Q2. The question, if we separate the two spheres away from each other, what do you think the charges will be on each of the spheres? Okay, so this is still an isolated system. Okay, and after they touch, and they are very similar spheres, assume these are metallic spheres, and then we separate them from each other. What do you think the charges will be on each sphere? You can use the chat or turn on your microphone.
They divided equally.
Exactly, they are divided equally. The symmetric situation, these are two Q1, so the charge of each sphere, they will be equal, and hence, so if we separate them, the total charge, and so now the next step is they are going to be separated. Okay, so the total charge is still Q1 plus Q2, but the new charges, let's call them capital Q1 and capital Q2, they will be just equal Q over 2. So notice now in this case, capital Q1 is equal to capital Q2 and is just equal to the total charge Q1 plus Q2 divided by 2. Okay, so the symmetric situation is because these are very similar spheres and metallic spheres, the electronic equilibrium that we will speak about in the future lecture will cause the charges to split equally between them. Okay, and so the charge is still conserved, the total charge is still equal to Q, which is Q1 plus Q2, but they just share the charges equally. Okay, so now we can accumulate or summarize physics 121 and physics 122. Remember, in physics 121, you studied that if you have an isolated system, okay, the energy is conserved, the total energy delta E. Remember, we had, if the system is isolated, delta E, which is equal the change in kinetic energy plus the change in potential energy plus whether it's spring or gravitation potential energy plus the change in thermal energy, E thermal. All of this is equal to 0 if the system is isolated. Okay, if the system is not isolated, you've seen that the total work, external work, done on the system is equal delta E. Okay, so this is the law of conservation of energy. Then later on, you study the law of conservation of momentum. If you have an isolated system, the momentum, the sum of the momenta before is equal to the sum of the momenta after the collision. So we had in an isolated system, we have conservation of momentum, and we wrote the general equation is that delta P. Remember, P is a vector, and so you can have momenta in X, Y, and Z direction. And later on, when you studied rotational motion, you studied the fact that the angular momentum is also conserved for an isolated system. And so if you remember well, if you have a person holding a dumbbell and rotating, if he brings the dumbbells closer to him, he will rotate at a faster speed. And we said that was due to the conservation of angular momentum. So we have conservation of energy, conservation of linear momentum, conservation of angular momentum, and now we added a very important new principle. If you have an isolated system, we also have conservation of charge. These are very powerful physics principles or laws that help us solve many problems. Any question about conservation of energy? Conservation of charge. All right, let's move to the next one. All right, so here, let me turn on well, let me, yeah, why not? Let's see, and show this card, and let me go here, and okay, so here's code. Okay. So we will answer this question using the Kahoot. Remember the Kahoot, we use it for attendance purpose. So please make sure you participate because I will use it for attendance. I don't have the other means of what's going on. Login. Okay, so okay, so let me play this Kahoot. Okay, and start. Okay, so please either run the Kahoot application in your, so you can use either QR code or you can just, if you have the application, you can use the PIN number 2552843. Remember, please use your ID number, the full ID number, not only the last number, the full ID numbers, because I will use it for attendance. Please make sure you use your ID number. All right, so we turn off the sound. Okay, so let me see how many do I have. Yeah, it looks like I have only 29 participants. So obviously some students did not join us. Okay, all right, so please everybody join. Okay, so let me let you start thinking while the rest are joining. The PIN number will still appear. Okay. Okay, so read the question and answer. You have 4 choices, A, B, C, or D. I'll give you a minute to do this. So you will not be able to enter your answers until I start the next, the Kahoot, and you will have only 20 seconds to enter your answer. Okay, I guess half minute is enough. Okay, so you'll get another 20 seconds. And so choose between A, B, C, and D. And when I start the Kahoot, okay. Everybody participate, please. Even if you do not know the answer, make a guess. Okay, so we have 12 have the correct answer, and we have 15 incorrect answer. Quite surprising. Okay, I just gave the example. All right. So let's see how we said a charge is conserved. So this is an isolated system now. Okay, so we can determine the total charge, Q total, in this case, is equal to QA plus QB. So minus 50E. Remember, E is 1.6 10 minus 19. We will so we have minus 50E plus 20E. So we have minus 30 times E, which is 1.6 10 minus 19. Okay. Now, when you touch them, the system is still isolated, and still Q is still equal minus 30E. Okay, but because these are similar spheres, similar conducting spheres, when you separate them, they will have, so let's say capital QA and capital QB. We know capital QA is going to be equal to capital QB, and the sum of the two, we know that QA plus QB is going to be equal to the initial charge, which is minus 30E. So clearly, QA is equal to QB is equal to minus 15E. So the correct answer is minus 15E. So this is the principle of conservation of charge. So you can see clearly there is some disconnection between understanding the principle and applying the principle. And that's the gap I want you to bridge. Okay, once you understand the concept, you should be able to apply it. So here is a simple case that where some of you did not find the right answer. I'm sure you understood conservation of charge, but you need to be able to apply your understanding to a real situation like the one we have just seen. Any question about this example? Okay, so please either turn on your microphone or enter your question in the chat. Okay. Okay, so here, let's see, I have, okay, clear, thank you. All right, so let's, there is a very, how did we come up, or how did we scientists come up with this E, 1.6 10 to minus 19, okay? There is a very famous experiment, so let me introduce you to this experiment, okay? So this experiment was performed in the early 1900s by a Millikan. I'm sure he lived more than three years, so there is a mistake in the date, it looks like. Maybe 1973. Okay, so what he did, he performed a simple experiment where he had an oil spray and he sprayed drops of oil. He knew what kind of oil and he knew the density of this oil. So when he sprays this oil, it gets charged by the spraying system because it's the drops are rubbing against the wall of the sprayer and they become charged. Okay, and so what he did, he made a hole. Let me see if I can switch this one here so I can write. Okay, so he made a hole in this. And the drops, they drop through the hole. So there is a top plate and the bottom plate. And he connected these two plates to a battery. Okay, so basically he established an electric field. We'll speak about electric field in next lecture. Okay, and he adjusted the voltage of the battery, and he until he saw the drop being suspended in air. and he had the suspension when the gravitational force, which is equal to mg, is equal to the electrostatic force, which is q times e. Okay, and so he was able to, knowing by using the microscope, he was able to observe the size of the drops. So he could determine the mass because he knows the density, and he assumed these drops are spherical in shape. So he could determine mg, okay? And from this, he was able to determine the charge, because he knows the electric field, because he knows the voltage of the battery, he knows what is the electric field, okay? And we will explain this later lecture. He was able to determine the total charge on each drop, okay? So this is a very ingenious experiment where he was able, initially he was actually monitoring the velocity of the speed of the drops as they're dropping, and he used kinematics. He used kinematics. V final is equal V initial plus AT, and so on. So he was able to calculate the charge that is accumulated on the drops. And he notes the following. He notes that the charges on the drops are always a multiple of a certain number, and that number he called it E, okay? So he discovered that the charge is quantized, and the value of the charge were always a multiple of E, which is 1.6 10 to the minus 19 coulomb. So the charge Q cannot be a fraction of E. It's always, it can be 0, plus or 1 E, plus or minus 2 E, plus or minus 3, and so on. So if somebody tells you the charge I measured is 1.35 E, you tell him there is something wrong. The charge can only be a multiple of E. It can be minus 2E, for example, or minus 10 to the power 3 E, or plus 10 to the power 4 E, but it cannot be a fraction of the electron. So this is a very famous experiment that Millikan did in the early 1900s in order to determine that the charge is quantized. So the charges occur in either positive and negative. The charge in an isolated system is conserved, but the charge is quantized. It's always a multiple of E, which is, so E is a constant. E is a constant. And actually, for this experiment, it looks simple, but he won the Nobel Prize in 1923 for this discovery. Okay? So the charge is quantized. The unit of charge is coulomb, and the smallest charge is 1.6 10 to the minus 19, approximately 1.6 10 to the minus 19 coulomb, and hence E is called the elementary charge. It's a constant, so we use this is a constant. Okay, and so if somebody writes a charge, it has to be a multiple of E, as we mentioned, and so it can be plus 12E, minus 60E. This is possible, but if somebody tells you it's 3.5E or minus 5.1E, you ask him, please correct yourself. The charge can only be quantized. Okay, this is not possible. Okay, now I'm giving you this definition a little bit early on because a charge and the current, I know you have heard about the current in a circuit. The current is defined as the flow of charge per unit time, or the so it's dq dt. So if you have a wire, okay, and the charges are flowing in this wire, okay, so let's assume charges are flowing in this wire. Okay, let's assume these are electrons. Okay, if you count per unit time how many charges are flowing, you are determining the current. So so you can say, if the dt is large, you can write that the current is delta q over delta t. Okay, so the amount of charge flowing per unit time. It's much easier now to measure the current rather than measuring the charge. So if you have an ammeter, you can measure the current flowing in a device. But so what they usually do, if you have a charged sphere, you connect it to a circuit. Okay, and it flows, the current will flow, so you are discharging the sphere, and as the sphere is discharging, you can measure the current, and hence, if you integrate the current, you get the total charge accumulated on that sphere. Okay, there are some devices, they're called electrostatic meter or electrostatic voltmeter, they can also measure the charge, but these are very rare and expensive. Okay, so that's why I decided to introduce to you the current, and this is very important definition that we will come back to later on. The current is really the derivative of charge with respect of time, or dq dt. Okay, so the 1 coulomb is equal 1 amp second, or we can say 1 amp. The current, the units of current is 1 amp. So this is for the current, the unit of current, and it is 1 coulomb per 1 second. That's why I decided to put the definition of the current, because it's difficult to understand the coulomb without the amperes. So 1 ampere per second, 1 ampere is equal 1 coulomb per second. Any questions? Okay, please feel free to stop me at any time and ask your question. Okay, now, you have seen this before. Atoms are made out of a nucleus that has usually protons and neutrons, and the cloud around the nucleus is the electron cloud. Okay, so the model we are protons are positive, and so they have a charge of plus. A proton has a charge of plus E, 1.6 10 minus 19 coulomb, and the proton is very heavy compared to the electron. Obviously, it's 1.67 10 to the minus 27 kilograms. Okay. Now, if the neutron is not charged, does not have positive or negative charge, and it's about the same mass as the proton. It has a mass of 1.67 10 minus 27, 675 10 minus 27 kilogram. However, if you look at the electron has a negative charge. It's minus E. It's minus 1.6 10 minus 19, and notice the mass is 9.11 10 minus 31 kilograms. So it's how much is it looks like more than 1,000 times less massive than the proton. So these numbers will come in handy in some problems. So you might as well, obviously you should memorize the charge of an electron, 1.6 10 minus 9, minus 1.6 10 minus 19, but the mass of the proton and the mass of the electron will come in handy in some problems. So remember, 1.67 10 minus 27, the mass of the proton, and 9.11 10 minus 31 for the mass of the electron. Okay, so you can see the mass of the proton is about 1,000 times the mass of the electron. Okay, and so this is the simple model. So we'll stick to the simple model of the atom, where we have the nucleus that has equal numbers, usually not always, equal numbers of protons and neutrons, but sometimes the number of neutrons and protons are not equal, and this is why we have what we call isotopes. They have the same, and they have different, the number of protons are the same, but they have the same different number of neutrons. Okay, and electrons. So if the atom is neutral, the number of electrons and protons are the same. So because these are minus E for each electron, for the proton is plus E, so they should cancel each other if it's a neutral atom or a neutral molecule. And so usually when we write the chemical materials, we write the symbol of the material, for example, helium, and the top number we use as a superscript before the name of the material. That indicates what we call the atomic mass number, or the number of protons plus the number of neutrons. So basically the number of nuclei in the nucleus. That's the atomic mass number. The atomic number is, in this case, 2. It's equal to the number of protons. And obviously, since it's a neutral atom, it should be also equal to the number of electrons, but not always. If for example, if you have a non-neutral, you have an ion, a positively charged or negatively charged ion, then the number of protons is not going to be equal to the number of electrons. Okay, so this is how we indicate the protons, neutrons in a molecule or in an atom. So an atom becomes a positive ion when it loses an electron, and a negative ion when it gains an extra electron. And so usually we can use either a plus to indicate that there is an extra electron, or minus. So it depends on the material. And it can be 2 minus and so on. So that's how we indicate the element is an ion, not a neutral atom. Okay, so you take the lithium, for example, the lithium atom, and you can count. It has 4 neutrons and 3 protons. Okay, so in this case, if we write helium, we should use helium. It has 7. The atomic number is and the number of protons is 3. Okay, and same thing also the number of electrons. So if we write, okay, so the total positive charge is +3, the total negative charge is -3. The net charge of this helium, lithium, did I say lithium? It should be lithium, not helium, sorry. Lithium, so we should write it as, okay, lithium 37, not helium. Okay, and so this is a neutral atom with equal number of protons and neutrons, protons and electrons. Okay, so if it loses 1 electron, it will become lithium plus. So it's 7 and 3 to indicate the number of protons and neutrons on the superscript, number of protons in red in the subscript, and to the right we can indicate the number of extra or electrons or deficiency in electrons. Okay. So now we're going to be speaking about, we already introduced how we can charge an object in an insulator, because we've seen how we can charge a balloon. Okay. Now, the materials are usually separated in conductors, and the conductor is a material that has free electrons that can move around. Okay, so it's made out of atoms and molecules. But the valence electrons are, or some of the valence electrons are free to move. So in this case, we can say this is a conductor, okay, and so these electrons are free to move, and we will see how we can charge a conductor, or we can have an insulator. So some of the conductors are metals, for example, gold, aluminum, and so on. So the human body is a conductor. We do conduct electricity. That's why when you touch the power, the outlet, the current flows through your body, and which is mainly water. Tap water is also conductive. Okay, and so you should avoid touching water and holding an electrical device. Okay, insulators, however, they are also made out of molecules, so they have protons and electrons, except the electrons are not free to move. They are held tightly to the nucleus of the atoms and or molecules, and that's why they are called insulators. They do not conduct electricity. And examples are glass, plastic, pure water, water that does not have any ion, any salts or anything. That pure water, distilled water, is non-conductive, pure distilled water. Okay. So for the conductors, remember the outermost electrons are loosely held by the nuclei, and they can move around. That's what conduction. And for insulator, the outermost electrons are tightly held by the nucleus, and they are not free to move. Okay, so let's see. All right, so these are the main categories, conductors and insulators, but also just for completeness, I would like to introduce you to some other categories. Okay, semiconductors, these are materials that are intermediate between conductors and insulators, and they are commonly used in electronic devices like silicon and germanium. So they can be doped. If you are in electrical engineering, you can see the diodes and so on. They can have P-type, N-type doping, so they can have So they, in certain conditions, they will conduct. A diode, for example, will conduct when it's biased with the positive voltage. It will conduct, but if it's biased with a negative voltage, the PN junction of the semiconductor will not conduct electricity. So these are called semiconductor materials. Okay, and there are what we call superconducting materials. These are materials, if they are cooled to very low temperature, basically they have no resistance to flow of current. So these they are called perfect conductors because their resistance, and I'm sure you've seen resistance, V is equal RI. You've seen the Ohm's law. The resistance is basically zero for these superconductors, and they are used in some devices nowadays. So I will stop here. I will ask you to, if you have any question, please let me know. Do you have any question about what I have explained so far? Okay, you can turn on your
Doctor, regarding the positive charge, like when the materials, how come like glass and wood like attract or repel, yet they are insulators?
Okay, that's a very good question. In fact, we are planning to answer that question in the next couple of slides. So hold on to the next lecture. I will show you how insulator become charges, even though they do not, they are not conductors. They are not conducting electricity. So hold on that question and remind me at the beginning of next lecture, we will explain how we charge insulators and conductors. I hope you can wait for the next one, okay?
Okay, no problem.
Okay, any other questions? Any other questions?
Doctor, I couldn't find the slides on the blackboard.
Sorry?
I couldn't find the slides on the blackboard.
Yes, I will post the slides because these are documents in being changed as I'm preparing lectures. I change them. So I will post the slides of that I have already presented, okay? Because I have some exercises in these slides, and if you get the answers before the class, then the exercise becomes useless. So what I will do, I will post either the slides without the solutions of the examples we will do, or at least the slides of the material that we have already covered, okay? So they will be in Blackboard. Any other questions? Okay, all right, so we will see you tomorrow. We will start with Blackboard, and if it does not work, we will move to Zoom again. Okay, thank you for attending, and I will see you tomorrow, inshallah.